Have you ever built a machine learning model that just doesn't work? It's so frustrating. Well, today we are tackling a huge piece of that puzzle, feature engineering, specifically for anomaly detection. We're going to break down exactly how you can design the right features to make your algorithms incredibly effective.
So let's start with the big question. You've picked a great algorithm, you've fed it your data, but it's just not catching the weird stuff you needed to catch. It's a super common problem. So, what's really going on here?
Well, here's the thing. A lot of the time, the algorithm itself isn't the problem. The real culprit? It's the features. It's the data you're actually giving the model. I mean, think about it. If your features don't make the anomalies pop, your model is basically flying blind. The quality of what goes in completely dictates the quality of what comes out. Okay, so that leads us to our first really big idea, what I like to call the feature effect. We have to start by looking at the actual shape, the statistical distribution of our data. And trust me, it matters a whole lot more than you might think. You see, a ton of the go-to anomaly detection algorithms out there are built on an assumption. They kind of expect your data to look like a nice symmetrical bell curve, a Gaussian distribution. But what happens when you plot your feature and it looks like this? Everything is scrunched up on one side. This kind of skewed data is a major wrench in the works for your algorithm. So, what do? The solution is actually pretty cool. We don't need to go out and get brand new data. We just need to reshape the data we already have. It's kind of like tuning a guitar before you play a song. We're just getting our features into the right key so the algorithm can really sing. And here's your toolkit for doing just that. These are really simple but super powerful mathematical tricks. You could try taking the logarithm of your feature, or maybe just a simple square root will do it. Or you can get a little fancier with a power transform. The whole idea is just to play around with these and see which one nudges your data closer to that perfect bell shape. And here is the payoff. Just look at this. On the left, that's our original messy, skewed data. But on the right, after we apply a simple log transform, wow, it's so much closer to that beautiful symmetrical curve our algorithm was hoping for. It just goes to show you how a tiny tweak can make a world of difference. All right, so reshaping your existing features is strategy number one. It's powerful. But what if the problem is bigger? What if your features are just missing something important? Well, that brings us to strategy number two, putting on our detective hats and hunting for our algorithm's blind spots with error analysis. Now, if you've done supervised learning, you know what error analysis is. It's just looking at your model's mistakes to see where it went wrong. We can do the exact same thing here. We need to manually go in, find the anomalies that our algorithm missed, and then dig in to figure out why. That why is where the inspiration for our brilliant new features is going to come from. So check this out. It's a perfect example. All those red X's are your normal everyday data points plotted on a single line. And that one little green X, that's our anomaly. See the problem here? It's just hiding in the crowd. Based on this one feature, our algorithm would look at that green X and say, nope, nothing to see here. It's totally invisible. So the million-dollar question is, how do we make that little green guy stand out? How do we give our algorithm the new perspective it needs to see that this point is, in fact, really, really weird? And the answer is, we engineer a brand new feature. By creating a second feature, what we're calling X2 here, we literally add a new dimension to our data. And all of a sudden, bam, that green anomaly is pushed way out from the rest of the pack. It's not hiding anymore. It's got this weird combination of values that makes it stick out like a sore thumb. Now there's absolutely nowhere left to hide. Okay, I know this can feel a little bit abstract, so let's bring it down to earth with a real-world example. Imagine for a second that you're in charge of monitoring thousands of computers in some massive data center, and your job is to spot the ones that are about to fail. So we start by monitoring the usual suspects, right? Things like CPU load and network traffic. And most of the time, they kind of move together. But then we start thinking, what about a really specific tricky failure? Like what if a single process on a server gets stuck in a crazy infinite loop? In that case, you'd see the CPU load go through the roof, but network traffic would be basically zero because the machine isn't talking to anyone. It's just spinning its wheels internally. Now that combination, that's our clue. So, how do we build a feature to catch that exact pattern? It's actually incredibly simple. We just engineer a new feature that's a ratio, CPU load divided by network traffic. Think about it. For any healthy computer, this number is going to be pretty normal, pretty stable. But for our server that's stuck in that infinite loop, this value is going to be astronomically huge. And just like that, we've created the perfect alarm bell for our algorithm. So we've covered two really powerful strategies. Let's wrap this up and put it all together into a simple, actionable playbook that you can start using on your own projects. So here it is. Your playbook really just has two main plays. First, shape the data you already have. Use those transformations, log, square root, whatever it takes, to get your features into a shape your algorithm will love. And second, create brand new features. Use that error analysis to go on a hunt for your model's blind spots, and then get creative and engineer new features that shine a spotlight on those weird combinations of values. At the end of the day, really effective anomaly detection isn't about chasing the fanciest new algorithm. It's about being a great detective. It's about creatively listening to what your data is trying to tell you. So the question I want to leave you with is this: what hidden patterns are lurking in your data, just waiting to become your next killer feature?